So the third section of the course here starts with 3 variable linear equations. Now to talk about 3 variable linear equations, I want to take just a second to review 2 variable linear equations. And of course, the 2 variable linear equations were any equation that when we looked at our XY graph, that when we graphed them, plotted them, they formed a straight line. And so we had some requirements for them. In order to be linear equations, there had to be some things that they couldn't have. 2 variable linear equations don't have powers except one. On the variables. We all know that x is really x to the power of 1 and y is really y to the power of 1. But other than that, there were no powers, no squareds, cubes, no square roots. A root is a power. Second, the variable is not in the power. We couldn't have y equals 2 to the power of x or anything like that. And finally, we couldn't divide by a variable. Well, and those same things are all very true of our 3 variable linear equations. There are no powers on those variables other than 1. The variables do not multiply each other at all. They're not combined. They're all separated, and we're not dividing by any of the variables. In our 2 variable system of equations, our solution was expressed as an ordered pair, x and y. In our 3 variable system of equations, or 3 variable equations, our solutions to that three variable equation is going to be an ordered triplet. X, Y, and Z. Sometimes pronounced ordered triple, sometimes pronounced ordered triplet, sometimes pronounced ordered trio. All those words mean the same thing, 3, and their order matters, X, Y, Z. So an example might look something like this. Y equals 3x plus 5z. Notice no powers on any of the variables. 2x minus 4y minus 3z equals 21. Those would be linear equations in 3 variables. Ones that would not be might look like this. Y equals 5xz. That is not a linear equation because you can see the x and the z are multiplied together, which would require us, as we try to get them alone, isolate them, it would require us to divide by either x or z, and that would not be acceptable. (2x minus 5y plus 3z squared equals 18). Of course, there's a z squared there. That's not going to be a linear equation. Graphing in 3 variables is a little bit tricky, and it requires a little bit of an exercise in visualization. 3D visualization to be exact. And it can be kind of tricky. You know, we're used to the x, y plane where we've got x and y, and it's laid flat like that. But now we've got to bring a third dimension. Well, we can't come straight out of the page at us or out of the screen at us. So what we do is we take that xy plane and we back off and kind of look at it from off to the side. You might be able to imagine looking at it something like this. This is x and this is y. We've kind of pulled back and gone off to the side, so we're looking at it from an angle. But this is still just this xy axis system that we had before. And now the z-axis comes straight up out of the middle, like that. Now, if you stare at that long enough, you might be able to force your mind to see it in 3 dimensions, but it's really tough. Plotting a point is even tougher. Let's do the ordered trio 3, -4, 1. The only way we can plot that point on a 3-variable system like this, or 3-variable coordinate system like this, is to actually basically draw a box. X equals 3. So I go on the x-axis, 1, 2, 3. So I know that's where it's going to be on the x-axis. Y equals -4. So if I assume this is the positive y up here, positive x, this is the negative y over here. So I'm going in the negative 1, 2, 3, 4. So that's where it's going to be on the y-axis. And z equals 1, so positive 1 is up there. What I would have to do to plot this point is to basically draw boxes or rectangles, parallelograms, however you want to look at it, between every pair of axes. So between the z and the x-axis, that's probably the easiest one because it's just a square or a rectangle. Between the x and the y-axis, it's a parallelogram. This side over here is parallel to the y-axis. This side down here is parallel to the x-axis. And then the same between the z and the y. This is parallel to the y-axis. This is parallel to the z-axis. And now I just complete the box like that. This point right there is 3, -4, 1. Well, even plotting a few points on this coordinate system would get very, very cluttered because you'd have to have all those boxes drawn so you could see where they connect with the axes. It's just not practical to do a lot of plotting of points in a 3-variable system. Now, if you're in CNC, machining, map making, topographical map making, and stuff like that, you do need to have all 3 of those coordinates. It's just really tough to map them out. So what we're going to look at, if you wanted to graph a 3-variable equation, unfortunately, in 2 variables, a linear equation created a line on our graph. That's because it was a 2-dimensional graph. It reduces it to a single dimension. Unfortunately, in 3 variables, since you have 3 dimensions, the linear equation actually is a plane. So if I drew our axes here, that's my x-axis. That's my y-axis. That's my z-axis. And I have the equation 2x minus 3y plus 4z equals 12. We're going to stretch my artistic ability here, and I'm going to try to draw a plane on the graph here. The x-intercept, just like it was for two variable equations, if they're in standard form like this, the x-intercept is going to be our constant divided by the x-coefficient. 12 divided by 2 is 6. That's the x-intercept. The y-intercept is the constant divided by the y-coefficient. 12 divided by -3 is -4. So that's the y-intercept. The z-intercept is that constant divided by the z-coefficient of 4. So 12 divided by 4 is 3. That's the z-intercept. So our plane goes through those 3 points. And of course it extends out in all directions, but that triangle is the best way I know to illustrate that plane going through the graph. So really graphing the 3 variable linear equations is not a practical exercise either. The reason I'm going through all this is our next step is going to be to look at systems of equations. If you recall, 2 variable systems of equations we had things like 2x plus 5y equals 13, and 3x minus 2y equals 10. And we're asked to find x and y. And we had 3 different methods that we used for that. One was graphing. The second was substitution. And the third was that addition or elimination method. And in all of them, the goal, at least in the algebraic methods, the substitution and the addition method, was to reduce this system of 2 variables and 2 equations, to reduce it to 1 equation with 1 variable. Because once it was down to a single equation with a single variable, then we knew how to solve it and get the numerical value of that single variable. Well, now we're going to be looking at 3 equations, 3 variables. So they might look something like this. To solve it, those methods we used before are all on the table. Graphing would work if we had some way of graphing them exact enough so that we could find out what that solution was. But unfortunately, we don't. Without using technology to graph, we don't have a precise way of graphing. So graphing's out of the question. Substitution, however, works great, and the addition or elimination method works great. And so those are the two methods we're going to focus on today. Tomorrow, we're going to look at a method more on the electronic side of things, how computers and calculators work with systems of equations. We're going to look at matrices, which is going to be an additional method, an additional tool for solving these systems of equations. So anyway, let's take a look at how we would solve this system of equations with substitution. We're going to start with that. For ease of reference, I'm going to label my equations A, B, and C. Remember, the first step in substitution is to solve one equation for one of the variables. So here we have all three of these equations actually have variables that they would be easy to solve for. And some of them have multiple variables they'd be easy to solve for. Equation A, we could solve for any of the variables. So I'm going to choose equation A. I'm going to solve it for x. Now, why did I say that it would be easy to solve? Well, because there's no coefficients on the variables. Remember when we talked about two variable systems, if we're looking for a variable to solve for, we either want to find an equation that has a variable with no coefficient on it, so we don't have to divide by anything, or we want to look for ones that have easy things to divide by, like 2, 4, 5, 10. Those are all things that when we divide, we get an easy decimal, unlike 3 and 6 and 7, where we get repeating decimals, so we would have to stick with the fractions. So here we're going to solve equation A for x. So that means we have to get x by itself. To do that, I have to subtract y from both sides to get rid of it, and I have to subtract z from both sides. So y will cancel out and z will cancel out over here, giving me just x equals, on the right side, 6 minus y minus z is just 6 minus y minus z. That is my refined equation A. The second step is we're going to substitute that into the other two equations. So let's come back up here. Equation B. I'm going to replace x with 6 minus y minus z. Then I still have minus y plus 2z equals 5. Now there's obviously some things we can combine here. We've got the 6. We've got minus y, negative 1y, and another negative 1y make what? Minus 2y. Good. Negative 1z and positive 2z make? Z. Just z, so plus z equals 5. And my last thing I will do here is I will subtract 6 to get the variables alone on the left side. So I've got negative 2y plus z 5 minus 6 is a negative 1, so equals negative 1. So that is my modified equation B. Now the only equation I haven't used yet is C, so let's go back and do that. In equation C, again, I'm going to replace x with 6 minus y minus z. So 2 times x becomes 2 times 6 minus y minus z. Then we have minus y minus z equals negative 3. Now we've got the 2 here in front of the parentheses. We have to distribute that. 2 times 6 is 12. 2 times negative y is negative 2y. And 2 times negative z is a negative 2z. We still have the negative y and negative z sitting there. So now let's combine. The 12 doesn't have anything to do. We got negative 2y and negative y make negative 3y. Negative 2z and negative z make negative 3z equals negative 3. Now I'm going to get the variables by itself. I'm going to subtract 12. I have negative 3y minus 3z equals negative 3 minus 12 is negative 15. Now when we did our 2 variable systems of equations, we saw that we could multiply or divide a whole equation by the same number, and it didn't change the values of the variables. Right now, what I have done is I have created a 2 variable system, 2 equations with 2 variables. I've reduced this from 3 equations with 3 variables down to 2 equations with 2 variables. That one and this one. I could simplify this equation here because every term in that equation is divisible by negative 3. But rather than dividing it by negative 3, I'm going to divide it by positive 3. The reason I'm doing that is if I divide it by positive 3, the z is going to end up being a negative 1. Why would I want the z to be a negative 1? Well, then it'll cancel with the positive z. So let's do that. I'm going to divide this here. Negative 3y divided by 3 is negative 1y or just negative y. Negative 3z divided by 3 is just negative 1z or negative z. Equals negative 15 divided by 3 is negative 5. This top equation, I'm going to leave it just as it is. I'm going to bring it down. So 2y plus z equals negative 1. So now I have a system of 2 variables and 2 equations, and I can solve that however I want to. I could use substitution. I could solve one of them for y or z, or this one is perfectly set up to use that addition method. Negative y plus negative 2y is negative 3y. Negative z plus positive z is 0. It cancels out. Negative 5 plus negative 1 is negative 6. Now I can solve this. I have reduced that from 2 variables and 2 equations down to 1 variable in 1 equation. And now I can solve it. I simply divide by negative 3 to get y alone. Y equals 2. Now we have a considerable amount of work to go back up through the steps to find the other variables. I know that y equals 2, so I go back to one of these 2 equations to find what z is. I'm going to use this bottom one just because the z is positive there. So negative 2y plus z equals negative 1. I'm going to put 2 in for y. So this becomes negative 2 times 2 plus z equals negative 1. Negative 2 times 2 is negative 4. So we have negative 4 plus z equals negative 1. And now to get z by itself, I add 4 to both sides. Z equals negative 1 plus 4 is 3. Any questions? Now we got to find x. To find x, we go back to one of the original equations. I'm going to go back to equation A, the top one, which was x plus y plus z equals 6. And now I know y equals 2. So x plus 2. And z equals 3. So plus 3 equals 6. Well, we add the 2 and the 3 to make 5. So x plus 5 equals 6. We subtract 5. X equals 1. So now we have x equals 1, y equals 2, z equals 3 is our ordered triple. What do you think? Not so bad? No? Cool. So what's really happening here is as we said, each of these equations actually forms a plane on the graph. One equation might form a plane that looks like that. If the next equation forms a plane, how do those 2 planes intersect? What's it going to look like where those 2 planes intersect? Think of 2 pieces of paper coming together. When they intersect, they're going to intersect in a line. They're going to cut through each other in a line. So that third equation forms a third plane that cuts through. That third plane intersects, let's say the green plane will intersect the black plane in a line, and it'll intersect the blue plane in a line. Well, all 3 of those planes better intersect in a common point. So those 3 planes intersect to make these lines. Those 3 lines of intersection intersect in a common point. That is our solution to the system. However, it's not always that simple. There are other things. These planes don't have to intersect in a single point. You could have two of the planes parallel and the third plane cutting through both of them. So now we have two separate lines of intersection. That's not going to have a solution. That's going to be inconsistent. There is no single ordered triple that solves all of those equations. We might have all three of the planes. That's kind of a poor drawing. I'm going to draw an end view of it, just because that's the extent of my artistic abilities. If you look at it at the end, all three of the planes might intersect in a single line. So they basically form a rotary. And so in this case, the line is the solution. The planes could intersect like this in three separate lines, basically forming like a triangular tunnel. If you looked at it from the end, it would look something like this. Or, and again, there's three separate lines of intersection. There's no single point that makes all three equations true. Or there could be no intersection at all, where all three planes are parallel to each other. So again, there'd be no solution. So of all these cases, three of them give us no solution. One gives us that the solution is a line, and one gives us that there's a solution is a single point. Those are the ones we're going to mainly focus on, are the ones that give you a single point, but we are going to encounter those that give us a line or no solution as we go through them. Well, that was the substitution method. Let's do one more example of substitution before we move on to elimination. So we got 3x plus y minus z equals 2. X minus 2y minus 2z equals 6. 4x plus y plus 2z equals 7. Now once again, for ease of reference, I'm going to label these A, B, and C. Our first step is always pick one of the equations and solve it for one of the variables. Here there's one equation that's, all of them have at least one variable they would be easy to solve for. There's one equation that really sticks out that would be easy to solve for x. That's equation B. I'm going to solve equation B for x. I could have solved equation A for either y or z, could have solved equation C for y easily, but I chose B. And the reason for it is because I know just by experience that's going to give me all positives to work with. So x minus 2y minus 2z equals 6. I need to solve that for x. I'm going to get rid of the 2y by adding 2y to both sides. And I'm going to get rid of the negative 2z by adding 2z to both sides. So over here, the negative 2y and positive 2y cancel out. Negative 2z and positive 2z cancel out. So I have x by itself on the left side. On the right side, 6 plus 2y plus 2z is simply that, 6 plus 2y plus 2z. That is my modified equation B. I have to substitute that back into each of the other equations. So let's go with equation A. So 3x is going to become 3 times, I'm going to replace x with 6 plus 2y plus 2z. Then I still have plus y minus z equals 2. Of course, we're going to distribute the 3. 3 times 6 is 18. 3 times 2y is 6y. And 3 times 2z is 6z. Now I'm going to combine. The 18 has nothing to combine with on the left side. 6y and y make positive 7y. 6z and negative z make positive 5z. And that equals 2. Last step. Subtract 18 from both sides. So I got 7y plus 5z equals a negative. 2 minus 18 is a negative 16. That's my modified equation A. Which equation have I not yet used? C. So let's look at C. 4x, well, instead of x, it's going to be 4 times 6 plus 2y plus 2z plus y plus 2z equals 7. Again, I just replaced x with 6 plus 2y plus 2z. Now we'll distribute the 4. 4 times 6 is 24. 4 times 2y is 8y. 4 times 2z is 8z. And we have the plus y and the plus 2z equals 7. Combining now, nothing to combine with the 24. 8y and y make 9y. 8z and 2z make 10z. And it still equals 7. Last step, get the variables on the one side by themselves, so I'm going to subtract the 24. So I got 9y plus 10z. 7 minus 24 is a negative 17. That's my modified equation C. Those two equations now make up my system of two equations with two variables. So there is my two-variable system of equations. And it is not necessarily pretty. But I can make them, I can use the addition method to make them cancel. I'm going to leave the bottom equation alone. I'm going to leave equation C just as it is. The top equation I'm going to multiply by negative 2. So what's that going to do? 7y times negative 2 is negative 14y. 5z times negative 2 is negative 10z. Equals negative 16 times negative 2 is a positive 32. The bottom equation, C, we said we're going to keep as it is. So that's just 9y plus 10z equals negative 17. Now at this point, it might be apparent why we multiplied that top equation by negative 2. Because now we got a negative 10z and a positive 10z. They're going to cancel out. So I got negative 14y plus 9y is a negative 5y. Negative 10z plus 10z cancels out. It's 0. Equals 32 plus negative 17 is 15. Now we're down to a single equation with one variable. We solve it by dividing by negative 5. Y equals 15 divided by negative 5 is negative 3. Now we go back to one of these equations, or two variable equations, and solve for z. It doesn't matter which one we use. Somebody pick A or C. I heard A, so let's use A. 7y plus 5z equals negative 16. We're going to put in that y equals negative 3. So 7 times negative 3 plus 5z equals negative 16. Seven times negative 3 is a negative 21. Plus 5z equals negative 16. And now we're just solving. We'll add 21 to both sides. 21 cancels out. 5z equals negative 16 plus 21 is 5. Then we divide by 5 to get z by itself. Z equals 1. So we've got y equals negative 3 and z equals 1. We have to go back to one of our original equations to figure out what x has to be. It really doesn't matter which one I use. I'm going to go back to equation B just for the fun of it. Equation B was x minus 2y minus 2z equals 6. So the x isn't going to change, but the y we're going to replace with negative 3. And the z we're going to replace with 1. So now I'm going to treat this as a negative 2 times negative 3, which is a positive 6. Negative 2 times positive 1 is still negative 2. I'm going to combine. 6 and negative 2 make positive 4. So it's x plus 4 equals 6. And then subtract the 4. X equals 2. So we have x equals 2, y equals negative 3, and z equals 1. Any questions? Okay. That's substitution. Let's look at elimination. Or addition or elimination, I should say. So, in the addition or elimination method, I'm going to give you a system of equations here again. I'm looking for one of my examples that's going to work well with this. I used my best example already, but that's okay. I'm going to do, we'll do this one. 2x plus 3y plus z equals 4. X plus 5y minus 2z equals negative 1. And 3x minus 2y plus 4z equals 3. Once again, I'll label them ABC. Step 1, pick a variable to eliminate. In other words, to cancel. If I look at this one, I could do any variable, but looking at it, I see that z is actually going to be relatively simple to eliminate. Step 2, eliminate it in two different pairs. So here's what I'm going to do. I'm eliminating variable z. So the first elimination I'm going to do is going to look like this. 2 times equation A plus equation B. Why am I multiplying equation A times 2? Because if I multiply that by 2, the z is going to cancel out. So let's multiply it by 2. 2 times 2x is 4x. 2 times 3y is 6y. 2 times z is 2z equals, and we got to remember 2 times 2 times 4 is 8. We have now multiplied equation A by 2. Equation B we're going to leave just as it is, because equation B already has a negative 2z in it. So now when I add these equations, 4x plus x is 5x. 6y plus y is positive 11y. 2z plus negative 2z cancels out, equals 8 plus negative 1 is 7. There is my first two-variable equation. Which equation have I not yet used? Bless you. Which equation haven't I used yet? C. So I have to use C this time. Now it doesn't matter whether I use A or B with it. I'm going to do this. I'm going to do 2 times equation B plus equation C. So I'm going to multiply equation B by 2. The reason I'm doing that is that'll make this a negative 4. It'll cancel with the positive 4. So let's distribute the 2. 2 times x is 2x. 2 times 5, y is 10y. 2 times negative 2z is negative 4z equals 2 times negative 1 is negative 2. we have multiplied equation B by 2. Then equation C we're going to leave as it is. And we're going to combine these equations. We're going to add them. 2x plus 3x is 5x. 10y plus negative 2y is 8y. Negative 4z plus 4z cancels out. Equals negative 2 plus 3 is a positive 1. There's our second two-variable equation. So we've reduced this three-variable system of equations in 3 equations to 2 equations with only 2 variables. And now we have to solve that two-variable system. I am going to multiply this top equation by negative 1. Since both equations have a 5x in them, if I multiply that by negative 1, it'll give me a negative 5x, which will cancel with the positive 5x. So negative 1 times 5x is a negative 5x. Negative 1 times 8y is a negative 8y. Equals negative 1 times 1 is negative 1. The bottom equation we're going to leave alone. 5x plus 11y equals 7. Now we'll add these two equations. We'll combine them. Negative 5 plus positive 5x cancels out. Negative 8y plus positive 11y is 3y. Negative 1 plus 7 is 6. And now we can solve for y by dividing by 3. Y equals 2. I go back to one of these two-variable equations to get x. Doesn't matter which one I use, so I'll use the bottom one. 5x plus 11y becomes 5x plus 11 times 3 equals 7. 11 times 3 is 33. So 5x plus 33 equals 7.
Is it y2, not 3?
I put in 3. It should be 2. You are correct. Thank you. Yes, 11 times 2 is 22. So it's 5x plus 22 equals 7. Thank you. Now we solve that equation. Subtract 22. 5x equals negative 15. And then divide by 5. X equals negative 3. We still need to find z. I'm going to go back to equation A to find z. The equation A was 2x plus 3y plus z equals 4. So 2x becomes 2 times negative 3 plus 3y becomes 3 times 2 plus z equals 4. Two times negative 3 is negative 6. 3 times 2 is positive 6. Plus z equals 4. Well, when I go to combine here, negative 6 and positive 6 combine to make 0. So we just have z equals 4. So x is negative 3, y is 2, z is 4. There's our ordered trio. What do you think? Better than a sharp stick in the eye?
Yeah.
For now? It is a lot of steps. I realize this is 3 times the work of a 2-variable system of equations. Because you have to do the work twice. You do the elimination or the substitution twice, and at that point, all you've really done is reduced it to a 2-variable system. Now you have to do it one more time to solve that 2-variable system. So it is 3 times the work. If it was a 4-variable system with 4 equations, it would now be 6 times the work. You'd have to reduce that to 3 variables in 3 equations, then reduce that to 2 variables in 2 equations. I don't dislike you guys enough to make you do that. So we will see some electronic methods. Our matrices and stuff that we look at can be expanded to however many variables and however many equations we want to. You might have seen a pattern here. The number of variables equals the number of equations. If we have one variable, we can solve it with one equation. If there were 2 variables, we had to have 2 equations. Well, now that we have 3 variables, we'll need 3 equations. If you had 7 variables, you'd need 7 equations and a lot of free time. So anyway, we have the substitution, we have the elimination method. We're not going to have time to do a lot more examples of each of them, probably about 2 more systems maybe if we hurry here in the last 13 minutes. But sometimes you run into systems that are just designed to be easier to solve one way or the other. Let's look at something like this. We might have 3x plus 2y minus 5z equals 1. Um, 5x minus y equals 15. And you might have 4x equals 8. This is a full system of equations. There are 3 variables, there are 3 equations. But it's very simple because equation C here only has 1 variable in it. So here it's very simple to solve this using substitution. Remember, substitution, the first step is to pick 1 variable to solve, or 1 equation to solve for 1 variable. Well, here I can take that 4x equals 8. I can solve it for x. If I divide by 4, I get x equals 2. So I actually solve it and I get a number. I don't even get another expression that I have to put in. Now we can substitute that back into either of the other equations. Actually, we're going to put it into both. But the first one we're going to put it into is this one. Because if I put x equals 2 into that, I have 5 times 2 minus y equals 15. I can now solve it for y. Five times 2 is 10. So 10 minus y is 15. I subtract 10. I got negative y equals 5. We subtracted the 10 to get negative y equals 5. And of course, we have to divide by negative 1 to get rid of the negative to get y equals negative 5. So x equals 2 and y equals negative 5. We go back up to this top equation. 3 times x is 3 times 2, plus 2 times y is 2 times negative 5, minus 5z equals 1. 3 times 2 is 6. 2 times negative 5 is a negative 10, minus 5z equals 1. 6 and negative 10 makes negative 4, minus 5z equals 1. Get rid of the negative 4 by adding 4. Negative 5z equals 5, and then 5 by negative 5. Z equals negative 1. So we got there, x is 2, y is negative 5, z is negative 1. There's our ordered triple. Now that was obviously a very simplistic form, but we can have other systems of equations that are simpler like that. We have x plus 2y minus z equals 2. 3x plus 7y minus 5z equals 6, or x plus 2y equals 3. Now you can see here this bottom equation doesn't have a z variable in it, which is fine. So what would work best here is if I could find some way to eliminate z using the top two equations. I can actually use this one as one of my two variable equations because it only has two variables. So if I can combine these top two to get rid of z, and I'm going to do that by multiplying this top one by a negative 5. So negative 5 times x is negative 5x. Negative 5 times 2y is negative 10y. Negative 5 times negative z is positive 5z. Equals negative 5 times 2 is a negative 10. The bottom equation already has a negative 5z in it, so it's going to cancel the positive 5z, so I'm just going to leave that one as it is. Positive 3x, positive 7y, negative 5z equals 6. And we'll add the equations. Negative 5x and 3x make negative 2x. Negative 10y and 7y make negative 3y. 5z and negative 5z cancel, equals negative 10 plus 4 is, or negative 10 plus 6 is negative 4. There's my other equation. So now I'm going to use these two equations as my two variable system. I'm going to multiply that top equation by 2, so that I have 2x and negative 2x. They'll cancel out. Which gives me 2x plus 4y equals 6. So on bottom, I'm going to leave that the same. Negative 2x minus 3y equals negative 4. And we'll add. The 2x and negative 2x cancel. 4y and negative 3y make 1y, or just y. 6 and negative 4 make 2. So there it is, y equals 2. And now I can go back and put 2 for y into one of these other equations, into either one of these, to get x, and then go back to one of the other two to get z. What do you guys think?
Not too bad.
Like I said, it's just a lot of steps. Be careful with it. Homework 11A covers the material we talked about today. It'll be due on Monday, but I recommend you get it done today if you can. Tomorrow we'll look at matrices and other means of solving these. Remember, you have your tests back. I'll get yours to you in just a second. You can do corrections on them. Redo the ones you got wrong, turn them back in so you can get half your points back. Anybody have any questions? All right, you have a great day. We'll see you all tomorrow.